Our next speaker is Priya Donti. She's an assistant professor in the EECS and LIDS. She's also co-founder and chair of the Climate Change AI, which is a global nonprofit initiative to catalyze impactful work at the intersection of climate change and machine learning. Again, I'm butchering a lot of these because I don't have time to list all the accolades here, but I'll note that she's a recipient of MIT Technology Review's 2021 35 Innovators Under 35, which is quite a remarkable achievement. So please help me welcome Priya.
All right, thanks so much. Oh, do I have a clicker? Hold on. Maybe. Yeah, I'll just flip it on the laptop. So yeah, so we just heard two really fantastic talks, I think, talking about different ways that in order to kind of monitor global biodiversity change, in order to better understand how the climate is going to change, we really need to, or we really can benefit from the use of machine learning tools in a wide variety of ways. And so what I want to do during my slot today is try to give to step back for a little bit and give a bit of an overview of kind of, I think, all the, many of the very cool ways that I think machine learning is being used across climate change applications in order to help us kind of both, reduce greenhouse gas emissions, adapt to the impacts of a changing climate, and better monitor how the climate is actually changing. And then I want to talk a little bit about my own work in the area. And then given the sort of theme of the panel of kind of, again, computing for sustainability via sustainable computing, I also want to talk a bit about, as much as machine learning, I think it can be really helpful for climate action, also kind of the more complicated relationship, multifaceted relationship it really has with how we as a society approach climate change and what that means. And I just got off a red-eye flight this morning, so if I'm a little incoherent, apologies for that. So several years ago, a group of collaborators and I kind of sat down and said, we believe machine learning can be a useful tool for climate action. Several of us work in several parts of this area. But is that actually true? In what set of areas is that true? And what are the ways specifically that machine learning can help? Are there any themes we can see? And so we put out this paper called Tackling Climate Change with Machine Learning, which basically tried to provide an overview and assessment of ways that machine learning could help. And we saw kind of places where machine learning could play a role across virtually every sector of relevance to climate action, to helping us kind of reduce greenhouse gas emissions in the electric power sector or in buildings or in transportation, to help us come up with more targeted climate predictions, to help us adapt to the effects of climate change by helping us, for example, better monitor our biodiversity and health systems. And in the course of this paper, so for those who are interested, I would encourage you to check out the full paper. It is something like 100 pages, and so we go through dozens of applications, which I'm not going to be able to cover today. But we saw some common themes that recurred across these different sectors in terms of how machine learning could help, which I think give a kind of nice just overview of kind of the different things that can be done here. So one of the major themes for how machine learning can help is distilling large streams of raw data into actionable information. So you heard a lot about this in Sarah's talk, where we, for example, have huge amounts of biodiversity data captured in proxy sensors that are giving you proxies about this information, images and so forth. And so how do you actually turn that raw data into actionable information in situations where you can't have somebody sitting there and literally pointing out every animal in the Serengeti and identifying it for you? And so this theme of distilling raw data into actionable information actually comes up across a large range of climate change related areas. So there's a bunch of work using, taking satellite imagery and turning it into targeted information about who is producing greenhouse gas emissions at the entity level across the world and how much. And this can help with, for example, international climate negotiations. Or where is deforestation happening in real time across the world? Or what are the crop types of agricultural land so we can actually inform our adaptation strategies? And what are the energy efficiency characteristics of buildings where we may not actually have on-the-ground sensors? So there are lots of these cases where, in some sense, if you can get on-the-ground sensors, these are going to be the most accurate, these are going to be the most helpful. But in cases where you really do need to make decisions where you don't have access to this more targeted sensor information, analyzing large streams of data like satellite imagery, like text documents, can be a really, really important thing to do. Another theme that comes up is forecasting. There are many climate change related areas where having some amount of foresight helps you make a better decision. So on an electric power grid, for example, you are consistently playing this balancing game where the amount of power that's being produced on your power grid has to exactly equal the amount you're consuming at every single moment. And when you have, for example, solar panels and wind turbines that are hooked up to your power grid, whose output's varying based on the weather, you can imagine maintaining this balancing act actually gets harder and harder. So having the ability to have more targeted forecasts and more accurate forecasts of solar power, of wind power, allows you to actually balance your power grid better without having to resort to having too many backup fossil fuel power generators to provide your balance. And so machine learning has been used to actually take in, and this is another theme that came up earlier, multimodal data. So data of, you can take historical weather data, you can take images of clouds moving overhead your solar panels, you can take the outputs of numerical weather prediction models, and you can combine all of this stuff into a machine learning model in order to get a more targeted prediction of something like solar power production. And this theme comes up again, forecasting across many different areas too, including forecasting transportation demand and forecasting the impacts of extreme events. So both of these themes so far have to do in some sense with taking information and providing insight to a decision maker. There are also many places where machine learning can actually help with automated decision making, actually optimizing some kind of system. So for example, machine learning has been used to improve the operational efficiency of heating and cooling systems in buildings by basically taking in information about what the weather is like, what the temperature of the building is like, is the building occupied, and using that information to then say, can I come up with a better strategy to control the heating and cooling system in my building so that I'm maintaining various characteristics I care about, like the thermal, the comfort of the building, but you're still controlling the building in an energy efficient manner. And this theme again comes up across many places. When we think of heating and cooling systems, we often think of places we live, but this also comes up in data centers. This also comes up in food refrigeration systems. And it also even comes up in things like optimizing freight auctions, basically these large-scale game theoretic auctions where actually you decide how different goods are going to be transported around the world by what freight companies and what vehicles. You can actually kind of use these similar kinds of techniques to optimize freight auctions as well. Another theme that comes up is predictive maintenance, and this is one that often gets overlooked because it's a little bit less sexy as a topic. The idea is that we have a bunch of infrastructure. It breaks sometimes, and this creates various kinds of inefficiencies. And so the question is, can we actually try to predict ahead of time when a kind of outage or inefficiency may occur, and then preemptively address it, or at the very least, can we address an outage in real time? So the German rail operator Deutsche Bahn actually uses machine learning to analyze the sensors on the rail infrastructure in order to then understand, okay, is there going to be some kind of outage that's going to cause the trains to get delayed? And then they basically are able to fix that ahead of time. Now, those who have ridden the trains in Germany may still complain that the trains are often late, but they would be more late, I think, without machine learning. And so there's this aspect of kind of trying to make low carbon infrastructure more attractive compared to kind of high carbon infrastructure in this case. And so the last themes I've talked about, they all had to do in some sense with, we have some kind of system that's operating today, and we want to make sure that it runs more effectively. But there are also various cases where we're trying to discover next generation clean technologies, where we're trying to answer a scientific question about kind of how the climate will change. And actually machine learning can help there too. So for instance, when you're trying to create a better battery for your electric vehicle or for your power grid, how this usually works is that you kind of hypothesize about a particular design for your battery. You synthesize it, you test it out, you wait many months to see what the results are, you see what happened, and you try again. And you do this again and again, many design cycles of many months, and it can take years to design a better battery. So what machine learning has been used to do is analyze the outcomes of past experiments. Can we actually take our past experimental data and then use that to kind of predict or recommend future experiments that you may want to try in order to then increase the the probability that your kind of new synthesized battery will have good properties, and as a result kind of cut down the number of design cycles. And there are startups that have reported things like a 10 times reduction in the number of design cycles that companies they work with have had to go through to create that better battery. And then I won't kind of go into this in much detail because I think Abigail did a really great job in her talk talking about this. But basically, as we have large physics-based simulations that we often have to run, climate models, energy models, city planning models that tell us how kind of wind flows through cities and understanding the energy efficiency characteristics of these. We often want to represent more and more fine-grained processes or have more and more fine-grained outputs in order to allow us to make decisions. And kind of throwing all of that physics into the model would be computationally prohibitive. So we saw a great example of one way where machine learning can actually help us, in that case, to learn better parameterizations for these models. So across these different themes, I would say that there are kind of many places where out-of-the-box machine learning techniques can kind of work well today, but that there are also many ways in which our machine learning techniques have not been designed with the considerations in mind for like what are the real-world requirements of some of these areas we care about. So we heard about long tails, right? We heard about kind of this idea of needing to resolve physical processes and sort of merge physical knowledge with machine learning. And so my work also similarly tackles kind of one aspect of this, which is how do we create machine learning methods that can deal with physics and hard constraints associated with systems like power grids. And so I'm going to spend the next few minutes talking about some of my own work in this area. So my work is really focused on this idea of how do you decarbonize the power grid? Power grids, by which I mean this is the system through which electricity is produced, it's transported, and it comes to where we use it. That system of kind of generating and transporting electricity contributes about 1/4 of global greenhouse gas emissions. And as we start to try to do things like decarbonize the transportation sector by electrifying it, we all of a sudden are even more relying on a clean grid to enable decarbonization across many other sectors. And so the kind of strategy for decarbonizing power grids is, in general, to kind of plug in or use more low-carbon power. This can be nuclear power, but often is thought of as solar power, wind power, other forms of energy that vary based on the weather. And as you introduce renewables into the power grid, they have to interact with this really complex physical system. So it has all kinds of physics going on underlying it. So when you put power into the power grid, the power flows along the lines according to physical equations. There are all sorts of hard constraints you need to satisfy. So I can't get my power generator to kind of generate, if my power generator is generating no power in one moment, I can't get it to turn on instantaneously. There's some time that it takes for it to turn on. And there are various sorts of kind of electrical equilibria that the power grid needs to stay at. I need to make sure to not kind of disrupt my voltages, for example, too much. And failing to satisfy these constraints can lead to blacking out your power grid. So large-scale blackouts, loss of lives, things you really don't want to happen. And yet you have to satisfy all these physics and hard constraints as you're making all these complicated decisions on the power grid about how you schedule power, how you use power. And so as we start to introduce renewables into the system, we're basically needing to solve this problem at kind of higher temporal, kind of faster. Basically, if you have more variations due to renewables, you have to make decisions on a more and more real-time basis to deal with that. And at a larger scale, because we're plugging in more and more kind of distributed devices like batteries, like electric vehicles, and like smaller renewable energy sources. And so we have to now solve this problem at a much bigger scale. So how do we do this? Well, traditionally, you would use kind of traditional techniques from optimization and control to address this problem, where you basically write down all of the physics and engineering constraints you need to satisfy and then solve over them. And this is great because you know exactly, you know that your constraints are going to be satisfied. You know what you're getting on the other side. But as I mentioned, we're needing to kind of deal with this system at greater speed, at greater scale, and the optimization approaches are just not meeting that challenge at this point. It then becomes very natural to say, okay, well, let's completely just flip our approach. Let's try to use something like machine learning. We can take in a bunch of data, we can use that to automatically learn patterns, and we can output decisions very quickly. And this is great because you get speed and scale, But machine learning methods are good at optimizing for averages. They will do what you want most of the time, but then sometimes they will do exactly the wrong thing. They will fail catastrophically. And on a power grid, you really can't have that happen. You need them to satisfy physics and hard constraints. And so one question then becomes, how do you kind of merge these two schools of thought? How do you actually bring together traditional optimization and control and the safety guarantees they bring alongside machine learning? And so my group's work thinks about this challenge through kind of the use of a framework called optimization in the loop machine learning. The idea is basically, if you can write down the physics and hard constraints in the form of equations or optimization problems in many cases that you can embed into the design of your machine learning model, then now you get these nice hybrid methods that are learning from data, but have inbuilt knowledge or kind of enforcement of various constraints that you need to satisfy. And so the setup we're often looking at is you have a machine learning model, and we're specifically looking at deep neural networks, which are kind of at a high level, a bunch of functions composed together. And what we're saying is, instead of only using standard neural network functions, let's actually write down functions that represent the physics we care about, the constraints we care about, and embed them into our neural network as one of those functions, as one of the layers. And this paradigm can play out in a couple of different ways. So my group has looked at this question of, when you're creating forecasting models for electricity supply and demand, if you know they're going to make mistakes, how do you at least make those mistakes as non-critical as possible? So if I'm going to use my forecast of electricity supply to schedule, or of electricity demand to schedule how I schedule electricity supply, can I avoid under-predicting electricity demand at a critical moment where it would cause me to accidentally under-schedule electricity generation and as a result black out the grid? So what we do is we basically say, can we write down the decision-making process of scheduling electric power as an optimization problem and embed that within the objective function that our demand forecasting model is using to learn, and as a result, get a demand forecasting model that avoids making very bad mistakes when it comes to the perspective of what's helpful for the decision maker. We also look at things like, how do you actually better approximate some of the large-scale optimization problems that are used on power grids? For example, there's this problem called AC optimal power flow, which power grid operators use to actually schedule how much power their controllable power generators are going to produce, kind of based on how much demand there is at a given moment and based on the structure of the grid. And this problem is so expensive to solve that power grid operators actually use kind of a lower fidelity, lower quality version of it in practice. So we basically say, that's bad. If you're not properly representing the physics, you're actually making really suboptimal decisions on the power grid. So how do you instead use a machine learning model to approximate your power system optimization model and build in some stuff into the machine learning model to make sure that all of the critical constraints, that your physical representation of the underlying power grid is properly represented? And then we also look at this in the context of kind of reinforcement learning and distributed control. So you often have on the power grid all these distributed devices that you need to control. So you need to charge or discharge your battery. You have a solar inverter, so something that's hooked up to your solar panel that's sort of providing the interface between that solar panel and the power grid. And you can kind of modulate how that works to basically control how much of the solar power that's produced is actually going into the grid. So we have to control all these distributed devices, but we have to do this in a way that, again, respects the physics of the grid, that doesn't destabilize the power grid. So we've actually done some work to say we can leverage some insights from areas like control theory, which can actually give you provable guarantees on how your controller is going to behave, and embed those control theoretic specifications into the design of reinforcement learning algorithms. So you can get these reinforcement learning algorithms to learn to do something really nuanced from data, but still satisfy your control theoretic provable properties. All right. So the vision associated with all of this is that when we develop next generation machine learning methods, we often think of machine learning as this tool that gets sort of innovated on in the ether, and then we hope that the benefits of machine learning will trickle down to many different areas. And I think, as you've seen maybe evidenced even by the 3 talks you've seen so far, that's not true. There are lots of things, there are lots of kind of considerations and domain requirements like long tails, like physics, like constraints that you need to deal with when you're dealing with climate change related challenges that machine learning methods out of the box today are not necessarily satisfying. And so the vision here is really to develop kind of next generation machine learning methods that really respect the requirements associated with climate relevant systems, and in my case, really thinking about safety critical systems like power grids, like engineering systems, and like transportation. So in the last maybe minute or so, I guess I'd like to circle back to this idea that clearly, I think that machine learning is a really, really powerful tool for climate action, right? There's so many different ways it can be helpful, and fundamentally, to make aggressive action on climate change, we have to leverage every tool we have in society's toolkit. But I think it's important for those of us who work in machine learning to really understand that machine learning is not kind of, by default, a force for good. It is really a general purpose tool that's used in all sorts of ways across society, both good and bad. So for example, machine learning is used in many ways that explicitly increase greenhouse gas emissions. It's generated hundreds of billions of dollars for the oil and gas industry by helping to facilitate the extraction and exploration of oil and gas. And it's also used in applications like the Internet of Cows that facilitate bovine agriculture, which is also a very highly emitting activity. And so we have all these places where we actually have so much money across society going to using machine learning for highly emissions intensive activities. And because machine learning is an accelerator of the systems in which it's used, as long as we have a highly polluting society that is highly consumptive and growing in consumption, machine learning will disproportionately be used for these applications because that's where the money is. And we really have to think about this when we're talking to, for example, there's so much AI policy coming to the fore right now. We really need to think about this and make sure it's explicitly addressed in the way we actually think about regulating and practicing AI across society. In addition, there are lots of applications of AI and machine learning that we might not immediately think of as relevant to climate change, but that actually have huge implications for climate. So for example, autonomous vehicles are really potentially going to change the way our transportation sector works. But autonomous vehicles are often developed primarily to facilitate private, and these days fossil-fueled, vehicles, as opposed to facilitating, for example, public transportation or multimodal transportation. And that locks us into a particular way that our transportation sector looks, focused around private vehicles, that has a huge impact on how we think about decarbonizing the transportation sector. We have choices there, though. We can develop autonomous vehicles in ways that actually facilitate public and multimodal transit. And so sometimes these implicit choices we're making in our kind of non-climate related research can actually have huge implications for our climate trajectories. In addition, machine learning is really changing the way we consume information online, which has huge implications for the spread of climate information, as well as the way that we, for example, consume goods, things like on-demand delivery. And then last but not least, machine learning has its own computational and hardware footprint. So the hardware on which machine learning runs, right, it has materials associated with it, it was transported, it has kind of other embodied emissions associated with it. And the computation the actual computational cycles that machine learning algorithms run are powered by electricity. There's water used to cool data centers. So we basically really do need to think about the kind of energy, water, and materiality impacts of machine learning algorithms, which as we especially start to kind of go towards the use of larger and larger machine learning models with higher impacts here, we're really needing to be cognizant about how can we reduce those impacts, but also how can we make sure that we're leveraging any kind of environmental spend on machine learning in ways that are actually benefiting societal goals overall. And so for those who are kind of interested in some of the ways that these kinds of considerations can play out in policy, or what it is that kind of governments could be doing in order to address these issues, I'd encourage you to check out this report for the Global Partnership on AI, which basically talks about what is it that governments and international organizations should be thinking about in order to both foster the use of AI for climate action and align the use of AI more broadly by kind of reducing the negative impacts. And then Last, I'll basically close by saying, if you're interested in this general topic of AI and climate change, I would definitely encourage you to check out the Climate Change AI community. It is a kind of a place where people kind of working on AI-related topics, people working on climate change-related topics can come together to learn more about the area, find collaborators, potentially get funding, and otherwise kind of basically contribute to what I think is a really, really cool area. And so there are various kinds of reports, workshops you can submit your research to, summer school that you can also attend. So there are 3 summer schools you should go to this summer. And then as well as research funding, online community platforms, webinars, and ways to engage in policy-related stuff. So I definitely encourage you to check out the community. And so with that, thanks so much. And I'm going to hand it over to the next speaker.
Thank you so much, Priya. I know what I'm doing this summer now. I think.